Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this already we have discussed various topics. In previous session we have discussed about bending stresses in a symmetrical beams and shearing stress at a particular section in a loading beam whenever the beam is subjected to different loading. So how to calculate, how to formulate the equation for shearing stress we have seen. So in today's session, so the distribution of shearing stress in various sections of beams we will see in today's session. So before going to enter in the main topic, you should know about the course outcome. So here the course outcome is analyze the theory of simple bending for illustrating the distribution of bending stresses across the section beams under loading. So theory of simple bending already over. The students can explain about this simple bending and distributing for bending stresses across the sections beams under loading. They should be able to answer for this topics bending stress and shear stresses after completion of this module. So distribution of shearing stress. So first of all, in introduction part, we have obtained a relation which helps us in determining the value of shear stress at any section on a beam. Already in previous topic, we have derived that equation. So now we shall study the distribution of shear stress along the depth of the beam. Here, so determining the value of shear stress at any section on a beam already we have seen in previous session. So now we shall study the distribution of the shear stress along the depth of the beam. So for doing so, we shall calculate the intensity of shear stress at important sections of a beam and then sketch a shear stress diagram. Such diagram helps us in obtaining the value of shear stress at particular section along the depth of the beam. So now we shall discuss the distribution of shear stress over the following section. So different section beams, we will discuss the stress distribution. So the distribution of shearing stress, the following sections, one is rectangular section, another one is triangular section, and third one circular sections, and I sections, and T sections, and miscellaneous sections. What is the shear stress distribution in rectangular section? So take a rectangular section. And what is the shear distribution in triangular cross section and circular one and high section? And T section. So miscellaneous sections, if any is there, we will discuss. First we will see rectangular cross section. So distribution of shearing stress over a rectangular section. So consider a beam of rectangular section, that is A, B, C, D, of width and depth as shown in figure. This A, B, C, D rectangular section. So we know that the shear stress on a layer JK of beam at a distance y from its neutral axis. So already we have derived in a previous session, that is tau V is equal to force multiplied with A into y bar by I. So you know this equation. So D is the depth of the section and B is the width of the section. So let where here F is shear force at section, capital A is the area of section above Y, the shaded area AJKD, AJKD. So this is area of the section. Y is the distance of the shaded area from the neutral axis. And AY is the movement of shaded area about the neutral axis. Distance multiplied with the area. AY is the movement of the shaded area about the neutral axis. The I is the moment of inertia of the whole section about its neutral axis. The B is the width of the section. You know, for rectangular section, the I is BD by 1. For circular cross section, this is for rectangular section. For circular, pi dt for 4 by 60. See, we know the area of the shaded portion AJKD. So as shown in figure here, the shear stress distribution. So here we will get a shear stress maximum at its neutral axis. So here the area A is B into D by 2 minus 1. So the width and Y D by 2 minus Y. So that is for AJKD section. Take this the section AJDK. Sorry, KD. For this, the area is B into D by 2 minus 1. The Y bar, Y plus half of the distance D by 2 minus Y. So we will get, after simplification, 1 by 2 into Y plus D by 2. So first area, that is equation number 2. First equation is shear force, and second one and third one is dy bar. Substituting the above values of A and Y in equation 1. What is the equation 1? Shear force A into Y bar by IB. It's already written here. Now substitute in place of A, B by B into D by 2 minus 1. And Y bar half into Y plus D by 2 by IB. So now simplify this equation. After simplification, you will get F by 2A into D square by 4 minus Y square. You see, from the above equation, that shear stress increases as Y decreases. So the Y decreases, the shear stress increases. At point where Y is equal to D by 2, the shear stress is 0. Where Y is 0, the shear stress is maximum. In equation, F by 2I into write down in equation d square by 4 minus y square. This is shear stress. So the shear stress increases as y decreases. So at point where d by 2, y is equal to d by 2. Suppose in place of y, d by 2, substitute d by 2, you will get 0 here. So total 0. Where y is 0, the shear stress is maximum. The variation of shear stress with respect to y is a parabola. So that's why in the previous diagram drawn this parabola equation. See? So at a neutral axis, the value of shear stress is maximum. Thus, substituting that y is equal to 0. There is no distance. So the coins lie on a neutral axis. And I is equal to BD cube by 12. BD cube by 12, the moment of inertia. So now, calculate the maximum shear stress distribution is equal to F by 2I. So the maximum distribution shear max at y is equal to 0. So that the F by 2I into d square by 4. So in place of I, substitute BD cube by 12. So after simplification, you will get 3F by 2BD. So it's 1.5 times of average shear stress. So what is this average shear stress? Is the force per area. So the force is F and area is BD. So you can write in terms F by BD is equal to shear stress, average shear stress. So the maximum shear stress at a neutral axis is equal to 1.5 times of the shear stress, average shear stress. See, in triangular cross section, consider a beam of a triangular cross section ABC. So here shown the triangular cross section. The base is B and the height is H, as shown in figure. We know that the shear stress on a layer JK, the shear stress on a layer JK at a distance y from its axis. So that is shear force, shear F into A y bar by IB. So where the shear force at the section F is, and AY is the moment of the shaded area about the neutral axis, and I is the moment of inertia of the triangular section about its neutral axis. So for this, so the diagram shown here, the triangular cross section, we know that the width of the strip is JK. From similar triangles, one is ABC, ABC, another one is AJK, the shaded portion. So the B is B into Bx by H. The width of the strip, that is this portion, JK portion. So area of the shaded portion AJK is equal to half JK, that is width into height, that is X. So the JK is, you can write half Bx by H. of jk is bx by h. So now the area of the shaded portion ajk will get bx square by 2h. So and the 2h by 3 is for neutral axis to fx. So that is for triangle 2h by 3 from neutral axis to fx. So this is suppose this is neutral axis from its fx. 2h by 3. So the y bar 2h by 3 minus 2x by 3. So we will get 2 by 3 into h minus x. So the area of the shaded portion ajk, substituting the values of b, a and y in equation 1. So you know the equation 1 force into, it's already written in a y bar by I into b. So what is a here? A is bx square by h and y bar and then I into b. Substitute those values in this equation, you will get finally f by 3i into hx minus x. Thus, we see that the variation of shear stress with respect to x is variable. We also see that as a point where x is equal to 0 or x is equal to h, the shear stress is 0. At a neutral axis, where x is equal to 2h by 3, the shear stress by 3i into hx minus x square. Final equation here by 3i into hx minus hx minus x square. So in this, at x is equal to 0 or x is equal to h, the shear stress is 0. At neutral axis, substitute x is equal to 2h by 3. So substitute in this equation, you will get 2f h square by 27. Here again, substitute the I bh cube by 36. And substitute in this above equation, you will get the shear stress is equal to 1.33 times of average shear stress. That is, area is equal to bh by 2. For triangular section, the bh cube by 36, the moment of inertia. See? Now, for maximum intensity, differentiating the equation, second equation. and equating to 0. So what is the second equation? The equation is shear stress is equal to F by 3I hx minus x. So differentiating this equation and equating to 0. Differentiate with respect to x and equating to 0. You will get h minus 2x is equal to 0 or x is equal to h by 2. Now substituting this value of x in equation 2, the shear maximum is equal to F by 3I. So substitute the x is equal to h by 2 in equation substitute and you will get in place of I substitute bhq by 36 and finally you will get 1.5 times of average. Shear maximum for maximum intensity. In this calculated for normal. For maximum intensity, if you want maximum shear stress distribution, differentiate the equation and then substitute x is equal to h by 2. Clear? So that shear maximum for triangular section is 1.5 times of shear. In previous rectangular section, how much we got? 1.5. The rectangular section shear maximum is equal to 1.5 times of the shear. Now we will see in circular cross section. A circular distribution of shearing stress over a circular cross section. Take a circular cross section and also take the small portion of the section JK. Consider a circular cross section of diameter D as shown in figure. We know that shear stress on a layer JK at a distance y from the neutral axis. So the stress distribution drawn like this, the shear maximum occurs at neutral axis. So maximum shear stress will be occur in neutral axis only. Set this point at the y is equal to 0. So why you know that the shear stress on layer JK at a distance y from the neutral axis. So that the equation, the shear stress equation, write down F into AY by IP. So AY is the moment of the shaded area about the neutral axis. F is the shear force at the section. So I is the moment of inertia of the circular section about its neutral axis. So now take R is radius of a circular section shown in figure. So JK is the elemental section of the portion. It's a beam. The B is the width of the strip. That is JK strip. We know that the circular section, the width of the strip JK, how do you calculate? B is equal to 2 square root of R square minus Y square. So take this portion J, B, O. So this is Y and R. You want the B. So for this, B is equal to square root of r square minus y square. 2 square root of r square minus y square. So area of the shaded portion strip is, now A is equal to B into dy. A is equal to B into dy. So the moment of this area about the neutral axis, y multiply with area. The moment of this area about the neutral axis is ay. So area already we calculated here. So 2 into r square minus y square into dy multiply with y. So written written as one equation. So the moment of the whole standard area about the neutral axis may be found out by integrating the above equation between the limits y and r. So you will get total whole standard area moment. Say y bar is equal to y to r. The limits, lower limit is y and upper limit is r. So 2y into r square minus y square, the moment of area about the neutral axis at this y point. If you want to enter whole portion, you have to integrate the above equation. So now integrate. So you can write the 2 into square root of r square minus y square as b. This term you can write as a b. So now b into y into dy. We know that the width of the strip jk is equal to 2 square root of r square minus y square. So now squaring of both sides, b square is equal to 4 into r square minus y square. So now differentiate both sides of the above equation. So we will get 2b into db is equal to minus 2y into dy. So minus dy 8y into dy. So to the y terms, one side, left side, and right side b terms. Y into dy is equal to minus 1 by 4 into b into db. So substituting the value of y into dy in equation 2. Y into dy, so equation 2 here y into dy into b is the total shaded area moment. So now substitute ay into dy in equation 2. Integral b into y into dy is minus 1 by 4 into b into db, lower limit y to upper limit r. So minus 1 by 4 into integral y to r b square into db. We know that when y is equal to y, width b is equal to b and y is equal to r, width b is equal to 0. The limits of integration may be changed from y to r, from b to 0 in equation 3. So now write down one more equation. A y bar is equal to minus 1 by 4 p to 0. So the limitation y to The limits of integration may be changed from y to r and b to 0. Y to r and b to 0 here. And then I know the equation b square into db. So 1 by 4, 0 to b square dp, eliminating negative sign. So now integrate this portion b square into db, b cube by 3 into 0 to b. So b cube by 12. The ay bar is equal to b cube by 12. Now substituting this value of ay in our original formula for the shear stress. You know the original formula is shear stress into F into ay bar by ib. So ay bar is equal to, already you know the equation 2 into r square minus y square. Clear? So, or otherwise, here already ay bar calculate b cube by 12. So substitute the b cube by 12 here. F into ay bar by ib, that f into simplify the b square by 12. So the b is equal to 2 into square root of r square minus y square. So this is equation number 4. The f into, in place of 2 into square root of r square minus y square is equal to r square minus y square by 3m. So thus, you essentially see that the shear stress increases as y decreases. At a point y is equal to r, the shear stress is 0. Where y is 0, the shear stress is maximum. So we also see that the variation of shear stress with respect to y is a parabolic curve. We see that the neutral axis tau is maximum. So that's why you have drawn in first slide the parabolic curve. So substituting this y is equal to 0 and 5d to the power 4 by 64 in the equation. The I is for circular section already you know 5d to the 5d to the power 4 by 64. Now substitute in the equation, you will get the shear max is equal to 1.33 shear average. So the maximum shear stress in the case circular one is 1.33 times of shear stress average. For rectangular cross section and triangular section, the shear max is equal to 1.5 times of shear average. So like this, how to derive the distribution of shearing stress equations or a circular section and rectangular section and triangular cross section. So other sections are there in already we have seen in the second slide, I think. So in this rectangular section and triangular section and circular sections are completed. In next sessions, we will discuss about I section and T sections. If any miscellaneous are there, we will see in next session. So for this PPT, so I have taken references S. Ramamurthy Madhar and the textbook is Strength of Materials. And other R.K. Rajput, the material is Strength of Materials. The textbook is Strength of Materials. The third one, R.K. Bansal, title of the book is Textbook of Strength of Materials. R.K. Bansal other, publications are Lakshmi Publications. And then R.S. Kurmi and Gupta. Title of the book is Strength of Material. And the publishers are Chand and Co. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.